this talk is about correctness of compiler backends. And so to make sure we are all on the same page, so here's how a traditional compiler looks like. So we have a bunch of front ends. They take some programming language, produce the same representation, some IR. The optimizations rewrite this IR, and then the backend takes this IR and produces assembly. And so here we are wondering, is the compiler backend correct or not? And so what's in a backend? So traditionally, backends were quite simple things. So we're like a one-to-one mapping between some IR instruction and some assembly instruction. But these days, backends do all sorts of optimizations. So they are a bit of a compiler on their own. Okay, so they're super complicated things. And so we should ask, are these compiler backends correct? And the answer is, well, of course not. And you can replace compiler backends with any big program, and the answer is always the same, smiley, right? The backends in LLVM in particular have more than 1 million lines of code. So of course, the number of bugs that you have, it's non-trivial. Let me give you a real bug that we found. So this is some LLVM IR snippet. So it loads a vector with 16 elements, 1 byte each. It changes one of these elements and then stores back the whole vector. Okay. Now, if you are a smart compiler like LLVM, you issue this ARM instruction that essentially stores directly 1 byte. So you change the vector in place instead of loading, updating, and storing back. The problem is this instruction can store anywhere in memory because the index is not validated. And so, if the index is out of bounds, you can store anywhere. And what the LLVM IR specification says roughly is that if the index is out of bounds, you should produce a Poisson tensor, a Poisson vector, which does not allow us to generate assembly that stores anywhere in memory. Okay, and so LLVM was clearly wrong. So this is a bug, and it actually introduced a security vulnerability in a compiled program. And we reported this bug, and now it's fixed. And so it was fixed using this AND instruction that clips the index, so it doesn't store anywhere in memory anymore. It can still change some arbitrary element of the vector, but this is a correct refinement of yielding Poisson. Okay, so we turn to translation validation, which is a way to certify that what's going on is correct. So, so this is in contrast with compiler verification, where we need to prove the correctness once and for all for the whole compiler. Translation validation is much simpler, which essentially you certify that this particular compilation was correct, but you cannot make any guarantee about compilation of other programs. And so Alive2, kind of showed us in the past decade that you can make it practical. So Alive2 has already found hundreds of bugs in LLVM. It's actually a mandatory tool now. So when you open a pull request with LLVM, you need to provide a proof using Alive2 to get the patch accepted. And so this kind of shows that this technique works. And so this paper is about applying translation validation now for backends, because Alive2 focuses just on the IR optimizations. Now we go one level below. Okay, so in a nutshell, ARMTV, which is our tool, so takes this LLVM IR as input. We use LLVM to produce AArch64 assembly, goes to the lifter, which is the main contribution of this paper, which takes assembly and then describes the semantics of this assembly in LLVM IR, which may sound weird, but LLVM IR is also low level, so we use it as kind of as a verification IR. Then we use LLVM itself to optimize this IR. So we kind of rely on LLVM to not remove bugs from this lifted IR. Okay, it can introduce new bugs, that's fine, but hopefully it should not remove bugs. And then we take this input IR and the lifted IR, give to alive2 and check whether it's a refinement or not. Okay, so that's roughly how it works. I'll give a quick example. So we start with some IR function, we compile into assembly, and then our tool takes this assembly, produces a much larger IR, right? Because now you have all these bit fiddling things. There's also a bunch of redundancy, and that's why now we use the optimizer to shrink this. And then we ask whether there is a refinement relation between these two programs. Okay, so focusing now on the lifter. So if you want to write this lifter by hand, it's a lot of work because current CPUs have like thousands of instructions. And so it's going to be a lot of work, and the probability that it's going to be wrong is like 100%, right? So, so we didn't really want to do it by hand. So, but fortunately, ARM has a machine-readable spec, so, which is quite complete, okay? Being quite complete is good, but is also a curse because it has a lot of detail that is not interesting to prove the correctness of a compiler backend. So we use partial evaluation to remove a lot of the detail that is not interesting. For example, we are validating code to be used in user mode. So all these checks whether the instruction is running in kernel mode or user mode or whatever, like we can optimize those out. To give an example, so here we have a specification in this ASL language. This is a vector instruction, so it has a loop over the elements of the vector. And we take these and we generate this compressed version of the specification. And then essentially when we see an assembly instruction, for example, when we see these adds like with vectors, essentially we have a sort of interpreter that goes over the spec and generates these IR. And note that we don't have any loops anymore, but we are actually generating IR, which does vector operations. Okay, so besides checking, that it's generating the right assembly, it's also very important to generate that is ABI compliant. So ABI is that spec that allows you to link files that were compiled from different compilers and allows you to call a function and know what state is kept, what state may not be kept, right? And so bugs in this part of the code are really horrible because you may get one wrong bit somewhere and then you don't know where that wrong bit is coming from. So we also implemented checks to make sure that the ABI is being followed. And we found bugs in this part of the code of LLVM. And this verification is the style of rely guarantee, because when you call a function, you kind of rely on that function following the ABI, and then you need to ensure that the function you are verifying is also following the ABI. Okay, so now going a bit on the verification side. So we use alive2, so we didn't have to re-implement all the verification algorithms from scratch. But there's a little catch, which is the IR that the lifter generates is valid, okay? It's perfectly valid, but is not a refinement from the original IR. And the reason is assembly has a different memory model than LLVM IR, and it's not possible to express this memory model in LLVM IR, or at least not in a reasonable way, okay? I'll just give one example. So if we have this function where we store to P if P and Q are equal, otherwise we store to Q, what LLVM generates is just a store to Q, right? because when they are equal, it doesn't matter whether you store through P or Q. When they are different, you store through Q, okay? And LLVM is smart enough to generate that assembly. But if you lift that assembly naively to an IR store through Q, that's not equivalent to this program, okay? And this is about pointer provenance, so I think that's a long story for some other day. But it's essentially we cannot naively do that lifting. So what we did, we implemented a flat memory model in Alive2, and we extended the refinement check to be able to do refinement between programs using different memory models. And also importantly is the optimizations, because SMT solvers are not magic boxes. If you throw random SMT, they don't work. So when we start working on these, nothing was verifying, of course. And then we implemented a couple of optimizations to make it work. Okay, so just to conclude, hopefully I've convinced you that compilers have bugs like any other tool, but compiler bugs are a bit more scary because they can introduce security vulnerabilities silently in your compiled programs. So we caught actually the same bug twice because the bug was fixed in LLVM and then someone reverted the fix. And so we caught the same bug a few months later. And so I leave up to you whether that was an accident or not. And then translation validation is a practical approach to identifying bugs. So it works fairly well. So our tool, ARMTV, already found 45 bugs in the AArch64 backend, but also in the generic backend code. And so it just reuses existing verification framework, so we didn't have to implement all sorts of verification algorithms. And just to reiterate, checking ABI compliance is super important. There are a lot of bugs here, and they manifest in very weird ways. Okay, that's it. Thank you for listening.
Yeah, for questions, please.
Okay, nice talk. And I'm wondering if you can extract the backend specification from other architectures such as the x86 because they have table gen. Yes.
Let's see. Actually, we are working on a RISC-V implementation right now, but using LLVM table gen files is not sufficient because the semantics is not is not sufficient because they are don't care bits, there are all these other things that table gen does not, because table gen is a refinement from IR to assembly. Is not an equivalence, right? Mm-hmm. But what we want is the other way around, is a refinement from assembly back to IR, right? And so table gen, maybe you can have, can go a long way, but it's not sufficient.
Okay, so this work is mainly for ARM, right?
Yeah, if you can have a complete spec, it's fine. If you have a partial spec, then there are no miracles.
Thanks.
Hi, thanks for a great talk. I have a rather practical question. So you said you assume that you don't remove any bugs in your translation. Does that actually happen? Do you have an intuition? If you do remove it, I assume you just miss the bug. But since you're not verifying it, but validating, it's okay. But do you have an intuition how often that actually happens?
So that thing, is LLVM, and this is where Alive can actually check whether that optimization is correct or not. So, we have already used Alive a lot in LLVM, so I think by now we have a good understanding where the bugs are. So I'm not too concerned, but it's a theoretical concern, but I think practically, if you really want, you can run Alive there as well. Right? But just maybe a fun story is some years ago, we were cross-checking Alive using Z3 and CVC4 at the time, and actually Z3 proved an optimization correct, and we only found by cross-checking with CVC4. And this was a one character fix in Z3 that made, it was like some copy-paste error that made a live proven optimization correct. That was wrong. So things happen.
Okay, I get that. Thank you.
Let's thank Nuno.
Thank you.